So hello everyone and welcome back. As you can see, in this session we will go through the last module of this course, which is the dispersed flow simulations or the Lagrangian particle tracking simulations. I've been working on Lagrangian particle tracking for 4 or 5 years. I've done my PhD also on this topic, so it's really exciting to me. And I'm happy to share it with you, at least some of my knowledge in this, in the framework of the course, which is just as a crash course. I will go through a first layer of what is Lagrangian particle tracking, or how to run a Lagrangian particle tracking simulation. So this topic in CFD is quite big and is very branchy, let's say. So whether you dealt with it or not before in the past, you will probably come across it at some point in the future, and it's very handy to know how to run this type of simulations, but also understand the dynamics between the phases. So as you can see here, our problem is very straightforward, and I chose this simple geometry problem, but very complex flow dynamics actually. So as you can see here, it's a channel flow simulation, or as we call it, a periodic channel flow. And what will happen is that we need to advect the flow first, which is air or whatever the fluid that you need to advect. Once it reaches a fully developed state, or what we call a fully developed flow, and a fully developed flow in turbulence means that you have a statistically stationary turbulence. Let's say that the statistics of your turbulence are not affected by time anymore. What I'm going to show you today is just to develop the flow until it reaches a turbulent state, and we can see these turbulent eddies inside the domain. And once we have that state, we don't wait until the flow is fully developed, but you can definitely feel free to do so on your side. It's just that for the sake of relevance and also the time limit, I'm gonna show you how to develop the flow into this turbulent state. And then once you have a turbulent state, you can impose particles. But usually for benchmarking, what we do is that, just for your knowledge, we impose particles once we have the fully developed flow state. Otherwise, you don't really know what to expect from particles, because the flow is still adjusting the boundary layer, and you have let's say a profile of RMS values, and you need to have a clearer picture before you impose your particles. Otherwise they go everywhere. What I'm going to show you is just the movement of particles, how to insert particles in the domain, and after you insert particles, how to advect those particles, because they will take the background flow as a carrier flow, and then what they do is just that they follow the flow in case that they are smaller particles, and they will deviate from the flow path in case that they are bigger particles. But again, I'm not going to dive so much into the details of this. I'm just showing you a showcase, as we saw in the last modules, or as we saw together in the previous modules, that we're learning how to run this type of simulations. And with every module you have different boundary conditions, you have different type of flow topology. So with that said, let's go right away and jump into our terminal and see how the problem is set up. Okay, so I'm now inside my working directory. Jump inside tflows, and then I will go to test, and then we will open a new folder here, which is swarm. And swarm is a group of particles, or a cloud of particles. So our problem today will be the channel flow mentioned, and there are two channel flow simulations in this test case. One of them has the shear Reynolds number 150, which is a mildly turbulent flow, and a shear Reynolds number that's almost 4 times higher. And the case that we will work today with is 150. And I'm gonna show you, and I chose that case because maybe it develops turbulence a bit faster. So now we have the case setup. As I said before, we have always the domain file, and we have the control file. So those are the most important things that you need to have in this directory, or in any test directory, or in any running case, because then you have to construct the domain somehow to generate the mesh. If you're not taking the mesh from an external mesher, convert it inside, then you will generate the mesh obviously internally. And if you generate the mesh internally, then you need this .dom file, which is, refers to domain, and the second file is the control file, which has all the input parameters. Here, just for you not to be confused, we don't have two control files here because we have two domains. We have two control files because just for the sake of dividing the simulation into two phases. The first phase is to develop the flow, as I mentioned here, to develop the flow field, which is the carrier continuous flow field, fluid flow. And the second phase starts as, let's say, in a second step with a second control file, which is taking this carrier flow field and then imposing or inserting particles. We call them insert particles, as you will see in the user mod file. And then you advect these inserted particles and compute them with the domain. So let's go back, and I will show you what this file contains, for example, here. So control A flow is the control file that's needed for developing the flow field, or the fluid flow, the continuous phase. And you can see already that I commented this line here, which is the number of time steps. It used to be a big number, but I commented this line and I used only 400 time steps just to develop the flow into the turbulent state. So I'm gonna use only the flow once it's turbulent enough, and then we will impose particles already, because then you can have it as a practical case instead of waiting for all of this time. This time is only meant to have a fully developed flow that if you're interested in turbulent statistics, so you want to measure, let's say, shear stresses or velocity variances or covariances, and you want to validate this data with DNS or some experimental facility, then you will need the flow to reach a steady or a statistically stationary state, which is a fully developed flow, and then you need to run more or less this number of time steps. You can also go ahead and check for yourself if you need more or you need less, but this is from the past. I found that the convergence history will follow something between these lines. And now the starting time step for turbulent statistics is also something that's a bit irrelevant to this course, but I just leave it here. We will not reach that time step anyways, because you can see here in this control file, we have the maximum number of time steps is 400. So we're not gonna reach this anyways, but this is used to start gathering the turbulent statistics if you're interested in turbulent statistics, but in this case, we're not. This is the most important here, but it will be, let's say, more relevant in the second control file, which is starting time step for swarm computations. So this is the moment of computing particles or advancing the inserted particles in the domain. You will start really computing an additional equation for each particle, which is called the Lagrangian equation of motion. Again, not gonna dive into numerics or mathematics here because it's irrelevant to this course, and I'm sorry that I keep repeating this because there is so much to learn about particles, but this will come in a separate course that I will focus more on particles, and it will be, let's say, an advanced topic where I have a deep dive into particles. And if you're interested also, you can go ahead and check out this other course. But for this one, we're just seeing how T-flows works without diving so much into implementation and mathematical models. So the last one here is starting time step for swarm statistics. So it's something similar to turbulent statistics, but we're gathering the statistics of swarm, of the particles themselves. We're not only interested in the picture or in the qualitative picture of particles, of seeing particles advance in the domain, but we're also interested in the quantitative picture of particles. So meaning that we need to study also the RMS values of the particles and maybe compare them with the fluid to see how much they deviate from the behavior of the fluid, and also maybe measure some concentration profiles or whatever you can do with the discrete phase simulation in any CFD code, more or less. On the one-way coupling level, you can do here in T-Flows. And yeah, one last thing is that the code here considers by default that you have a one-way coupling, as I just mentioned, between fluids, between the fluid flow and particles, which means that you have the particles affected by the carrier fluid only, but the particles are not affecting the carrier fluid. So let's say you can consider these particles as low inertia particles and low concentration particles also. It means that if you imagine dust in the air, for example, this dust is carried by the flow, but it's not really affecting the flow field or the turbulence in the atmosphere. But if you have a stone, or you have a considerably big size stone, then it will fall down with gravity because it cannot be carried by air, and it has different time scale and length scale than the carrier flow, which is the air, and then it will definitely affect the flow field if you throw it by free fall, or if you throw it with an initial velocity, then it will affect the flow field around it, which is the continuous phase, creating vortices and eddies or a wake region behind it or something like this. And what we're dealing with here is just small particles that are carried by the flow field and not affecting the flow field, so they don't give a feedback to the continuous phase. And then you have here save results, and we are saving every 100 time steps. And swarm again doesn't really matter so much here, because in this control file we're only affecting the flow at the beginning and backup save interval. To save the backup files, it's on a big time, because we're terminating the simulation at 400 anyways. So let's go and check the second control file, which is file B. And in control file B, which is the control file for particles in the second phase of the simulation, you can see already here that the number of time steps are raised to 600, which allows particles to be affected in the domain for almost 200 time steps. So they start computing, or the solver starts to compute particles from time step 405, and then the simulation keeps going on until 600. And we're saving the swarm, or saving particles, a VTU for particles every 10 time steps, and we're still saving the fluid flow at 100 time steps, because it's less interesting for us to see from that moment on the fluid flow than it is for visualizing the particles' behavior. So now I will show you how to formulate, or how to specify the characteristics or properties of particles injected in the domain. First of all, you have a block like this, and this is the swarm related block. As you can see, it's already defined here as a template, but you can also see maybe there are other keywords that you can use in the all keyword documentation file. We have here a template that says particle tracking yes, which is a switch that activates the particle, or the Lagrangian particle tracking algorithm in the code that makes it ready to compute particles. The subgrid scale model here, I'm not going to dive into this, but in a quick word, this is a type of models that add, let's say, some type of stochasticity to the particles, because sometimes you're under resolving turbulence, and then you wanna make up for this under resolution, so you add this type of stochastic models to kind of enhance the solution a bit without refining the mesh very much. That's just in a simple way to describe it. If it's too confusing for you, you can ignore it for now. That's why I commented actually, but I just wanted to let you know that there is this type of models inside T-Flows. And then you have the swarm diameter, which makes sense. We need two main and most important things about defining a particle. The first thing is the particle diameter and particle density. Makes sense, right? Because you need to see the inertial force of this particle being advanced in the domain. So you have here the particle diameter. We call it swarm diameter. It it more or less judges the group, and swarm density, which is 1000 here as a water droplet, let's say. And then you have the number of swarm substeps. That's a good part because in order to advect particles in the domain, you don't really use the swarm time step. You don't really use the flow time step or the global time step, which is the one defined here. But usually you have the option, I mean, you can always use the global time step, which is just by putting one here, meaning that you don't divide the global time step into any subdivisions. So the particles can feel time steps in terms of half the global time step, because it divides by 2, and then it doesn't use 0.1 second. It uses half of that, which is 0.05 seconds for each particle. So it kind of advances the particle on 2 steps per flow time step, and that's for stability reasons, and that's a criteria that is used in almost every CFD code for particles. But yeah, again, that's irrelevant to dive into more details about this, but just for you to know that each particle would like to see if it will sense the flow time step or a smaller time step than the flow time step. And by this keyword here, you can identify, or you can specify what will happen. And here, max particles, this is the maximum number of particles. I put here 1000 just to have a practical case, but usually in a turbulent channel flow, you need to have more or less stochastic approach. Let's say you're interested to cover up the whole domain when you're studying particles in that sense, or in turbulent flow fields. In this way, I just added 1000 particles for tutorial, just to make the case run faster. The last keyword here is swarm coefficient of restitution, which is the coefficient that defines for the particle if it's going to stick to the wall or rebound from the wall. So once you have a wall for particles, the particle has to know what is the boundary condition for this wall. Is it a sticky wall, or what we call a sticky wall? And for a sticky wall, once the particle touches the wall, then it will stay there and it will be removed from computations, because it will be regarded as a deposited particle. But if this coefficient of restitution is 1, it means that you have a fully elastic, fully rebounding mechanism between the particle and the wall. It doesn't lose any energy, which is an approximated situation, but that's what it means. Those are all the keywords that you need to know about those two control files. And you have here readme first file, which explains exactly what I just mentioned, that you have 2 phases, or two steps of the simulation. One is to develop the flow field, and one is to develop the particles once you insert them. What I wanted to tell you here before we run the simulation is that and in a similar way to the previous simulations or modules, I've created also a run case, which is an automation script that can run the whole case for you without going through all the steps of generating the mesh and then dividing the domain and then running process. It does that all to you through some elegant, or I try to do it in an elegant way as much as possible, but you can always modify it if you find something that I didn't do in a good way. In some cases, we need to activate the compiler, or we need to activate the process. We need to activate the process and link the user mod function while compiling the code. And this is one of the cases. And what you can basically do to check if the case that you're running needs to be compiled with dir case, directory case, this option is just to have a look here, user mod. And obviously this is a case that I told you at the beginning that runs through 2 steps. One is the particle, one is the fluid flow, and one is the particles. Then you can see that user mod here is doing something. You can kind of guess it because you have insert particles, and insert particles is just controlling what happens in the second step after the flow is fully developed. So in this case, it's obvious that we have to go ahead to sources and recompile the code. So let's do make clean, make MPI, yes, and directory case goes to this swarm case channel flow with 150 shear Reynolds number. Let's go ahead and run it. Perfect. Now the case has run already, and now we can go back to our test directory, and we can go through run case quickly, which is the automation script that runs the case. But quickly, let's review something before we run this problem, because I formulated in a bit of a smoother way than the previous cases, because it has two phases, as I mentioned. So it will take from us two arguments at the same time. Instead of only parallel or serial, then similar to the previous cases, we run together. It will take the fluid state, or let's say the phase name, which is fluid or particles, and the second argument that will take it from the user is the run mode, will be either serial or parallel, obviously. So you have here the number of cores, and then you have the first argument will be either fluid, so if fluid, or if we go all the way, or particles. So you will this one, it's the first argument that you will input as a user. Then if it's particles, then it will run some commands. If it is fluid, then it will execute these lines. And as we mentioned before, you're cleaning the case from any possible old files that you might have in your directory, and then removing any output files here, just in case, because maybe you're testing something and then you forget that you delete the output file, and sometimes maybe you have a clash because your system doesn't allow overwriting this output file, and it has the same name because you're using the same script. But as I said, all of these things, these are just tools for you to make your life a bit easier, or you make the process runs faster a bit. But if you know what you're doing, you can always refine these commands, and then you can maybe generate your own scripts, no problem. And then you're linking the binaries here, that executables that reside inside binaries directory, generating the mesh, linking the control file, which is the first phase here. So we're linking the control file A, which is responsible for the fluid flow, to control. So the control, what T-Flows is expecting is just a control file, which will be the global one, and then it will ask you if you want to run in serial or parallel, completely like the last modules that we run together. Once you have the fluid flow fully developed, or in this case running only the 400 time steps that we prescribed, the simulation will be terminated, and then you need to run again the same command, but instead of saying fluid, you will say particles. If you run the first simulation in serial, then obviously you continue in serial. If you run parallel, then you run this in parallel. So let's go ahead and run the first phase, and I'm gonna do it this way. So we do sh run case, which is running just a script, and then the script, as I showed you, is expecting two arguments. The first argument defines the phase name, which is here fluid, and the second argument defines the run mode, which is parallel in this case, because we want to run in parallel. And I'm gonna put this and sign to protect our system, make it run in the background so we can visualize the results somewhere else. And then it gives us a live view of what's happening. So here we constructed the domain mesh, dividing the domain into 4, and then running now in parallel. So it's loading the solver, and then goes on, and it starts to compute the fluid flow. Here we're only computing fluid flow. You can see already the residual of momentum equation, and then the conservation of mass and the pressure. Then here you have K epsilon zeta. Those are just the residuals of the transport equations of the turbulence model used. If you open the control file of the fluid flow, I want to show you the turbulence model that's used here, which is the hybrid RANS LES. So that's a very sophisticated model that uses a good advantage of a RANS simulation, a RANS type of simulation, and blends it with an LES scheme into the bulk region. It makes the good thing from both worlds, let's say. But so it's a turbulence model that you can define in T-flows, and then if you're interested, you can go ahead and source code and see how this one is constructed, because there are so many hybrid RANS LES models in the literature. So if we go back to the simulation, I guess it will take quite some time. Click on the down arrow. Yeah, you can see that it started only now to save the results after 100 time steps as we defined. So if you want to visualize what's happening, you can list first what's inside your directory. And if you want to take the pview file, since we're running in parallel, so you can type paraview and then this pview file. Probably we don't see much because turbulence needs some time to evolve, but let's see if we can see something. Yeah, you can see already that the domain doesn't have any turbulence yet, so you need to wait a bit until you can see some turbulent eddies forming in the domain. You can see it looks like a laminar flow. It's actually not, but it takes some time to develop the turbulent structures in the domain. So I'm gonna get back to you once the simulation has run, and then we can discuss the results before running particles. Alright, so that the simulation has been finished, we can go ahead and visualize the results. So let's open paraview, and then we have now pview files, but we have also the boundary files, which are the results stored in the faces. But we're more interested in the internal mesh here. So we visualized already 100 time steps, which was before the turbulence develops. And then let's visualize the last time step now. And maybe we close off this so we can see the difference. So if we visualize the velocity field, you can see already that turbulence has evolved and probably on its way for being a developed flow. So we just stopped the simulation, as I said earlier, at 400 time steps, just for practical reasons, so we can inject particles and not wait forever. But at the same time, our purpose of having a turbulent flow has been achieved here, and we can already go ahead and insert particles. And as I mentioned before, that the pixelized imager, you have this view where every cell has only one color, and that is because these values are calculated at the cell center and they're not interpolated on the nodes. And if you want to have a smooth picture, which is an interpolated picture of the flow, interpolated values from the cell center to the node, then you can go and choose the filter, which is cell data to point data. So it can give you a smooth domain like this. Then you can of course play with the color palette, so you can maybe distinguish these structures in a better way if you want. So let's see like that. Yeah, more or less the same. You can see also in the top and bottom you can have these streaks, low speed streaks as we call them, that the turbulence is extending in this direction, causing what is named hairpin structures, or let's say low speed streaks, or these sweep and ejection events close to the wall. But those values are interpolated from the last cell center, which is the cell center close to the wall, onto the nodes. But this is not really the wall, it's just that the cell center interpolated on the wall, or on the node of the wall. If you want to visualize the walls, then you can go and choose maybe boundary. So that's the boundary, which is the wall face. And if you see this, you realize that the velocity here is 0, which is what you would expect, right? Because we have a no-slit boundary condition. So just that you're not confused when you have some streaks or some velocity distribution in the wall, you're not really looking at the wall, but you're looking at the closest cell to the wall, the proximity of the wall. When you interpolate this, you interpolate the cell center to the node, the closest node to the wall, but not the wall itself as a solid. Huh? So that's on the fluid side, and we're happy with this picture. I guess it's clear to you that the flow is turbulent already, and we are all set to start the particle simulation. So we can go back to our terminal. So now let's go ahead and run our second simulation, run case. Then we replace the first keyword by particles instead of fluid, and then we run in parallel. So running in parallel here is, it will automatically take the same number of processors, or the same number of cores, without even dividing the domain, because it's divided already. So what it does, it just takes the backup file, which is this 400, the latest solution, and then it will plug it in that it can restart the simulation from this, that the first time step will be computed as 401, and so on and so forth. So we put the and sign so we can protect our simulation maybe. So it says running T-flows in the dispersed mode, so dispersed flow simulation in parallel mode. So if we go here, starting really from 405 time steps, you will see that the particles are injected already. So you have this additional box here starting from 405, because we specified in the control file that we need to insert particles starting at 405 time steps, starting after five time steps from retrieving the solution, basically from the backup file. And what you see in this box here is just some stats about particles and what their situation is inside the domain. So total number of particles, number of active particles, just in case that you have some lost particles, then it will be reported here, or some deposited particles, as we talked about the sticky wall boundary condition, then it will be also subtracted from this number, which is the original injected number of particles. Then you can see here deposited will be incremented, and the escaped particles, just in case that you have any particles that has escaped the domain for some reason. Total number of reflections, if you it's a good stat to have some perspective on how active the particles are in case that you have a reflective boundary condition, a reflective wall, which we have now here, which we have in this simulation, putting the coefficient of restitution to 1. And then you have here some other statistics like the Courant number and Reynolds number and the Stokes number of the particle, which is a characteristic number about the particles that gives an idea about how heavy, quote unquote, this particle is compared to the background flow. So it's basically the time scale of the particle divided by the time scale of the fluid. And then if this Stokes number is high, then it's obvious that what we expect is that the particle would deviate from the flow, but that's another topic. It's just to give you some idea what these numbers represent. And now let's see where the simulation has progressed. Okay, so we have already 90 plus time steps are finished. Alright, so we have already our first saved result from 500, from time step 500. And now we can visualize it into ParaView until we have the last time step. So we're saving particles every 10 time steps. So we have actually lots of results for swarm. And what you need to focus on are these VTU files. We're running in parallel, yes, but the way I developed the swarm module is that it saves the files into VTU files anyways, whether it's a serial mode or a parallel mode. And the reason for this is that you can always impose particles without post-processing a lot, putting some filters here and there, and also that it's sufficient, just very sufficient for particles to have a VTU file without flushing results into each processor separately. And one last reason is that the processors are all in knowledge of what's inside the other processor's particle-wise. So for all of these reasons, I just flushed the swarm results into VTU files outside the subdirectories here, and also that you can visualize them a lot easier. So I would like to go to ParaView now, and I will show you here maybe, but instead of this domain, because maybe if you reduce the opacity, then you will see some kind of domain decomposition, and it's not maybe the clearest way to visualize particles. So I'm gonna switch those guys off, or maybe actually we can use the boundary file. Actually, that's a good way. Maybe we can start by this. We can use the boundary file, which shows the top and bottom walls, and we can visualize particles on top of that. So let's put swarm, and I'm gonna put 410, which is the first time step that the particle results were saved. And if we click apply, you don't see anything because you need another filter, which is glyph, and this glyph is usually used for visualizing particles. And what you need to do here is a couple of things, that you have a good representation of a particle. So maybe we can use sphere because they are spherical particles in essence, or at least the way that we simulate them here. So it's perfectly spherical and they don't change shape during the simulation. Then maybe you don't need to scale the array. And here, let's say with the scale factor, just from the experience, maybe let's add something like 0.02 and click apply. If they are too small, I guess particles are a bit too small, maybe we can put something like 4 maybe, or something. Now we can see. You can see already this beautiful picture of the particles dispersed all over the domain. I mean, they're not covering really the whole domain, but we just used 1,000 particles for now. And what you can do also to have a good representation, if this is not very clear to you, I'm gonna zoom in a bit. So maybe you can use here this coloring option. You can put them maybe in black or even maybe red here with this top and bottom walls, and you can see what's happening, right? So it's a good representation if you like it. If you don't, then you can maybe switch the boundary file off and go to maybe a VTU file. So a VTU file is just a geometry file that was created at the very beginning, before even dividing the domain into 4 subdomains. And if you hit apply, then you have the domain which contains the mesh also. So you have the whole domain which contains the mesh. As you can see here, we're refining towards the upper wall and lower wall to kind of treat, or I don't want to say resolve, because we're using here a hybrid trans LES. So we're using some kind of wall modeling, and we're not really resolving the boundary layer, but we're treating the boundary layer fairly enough to represent the velocity gradient. And what I wanted to show you here is that if you switch back to surface and you reduce the opacity, then you don't have any problem, right? You can maybe reduce the opacity to 0.2 or 0.1. And if you want to color it also, you can always use the coloring option. There are so many tools that are very useful here in ParaView. And then now maybe you want to switch back the glyph, which contains all the particles, so you can also visualize them in this way. So it's up to you really if you want to visualize it with the whole domain like this. You can see inlet, outlet, or the periodic boundary conditions, top and bottom walls, or if you want to do something like this. So it's completely up to you. Now, in order to see some motion of the particles, I'm not sure if it's maybe we're saving at a very high frequency or a very low frequency, but let's see. At least that I can show you that you can make a movie out of this, and it can be really nice to see how particles are traveling in the domain. So what we'll do is maybe you can switch those off. Then we don't have the particles for this time step, but we will have, or we will load all particles for all time steps. And what we need to do for this is, as I said, it's VTU file, not PVTU. And if we go down all the way, so the simulation has been terminated already. If we go back to the terminal, I can show you already that the solution is not progressing anymore because the simulation has finished. So So we have the time step. Let's go back. No, it doesn't give you the last time step, but tells you that that you have already the time step 600 has been saved and terminated. But if we go inside the output file, let's say particles, and then if you type colon the dollar sign, sorry, it brings you to the last page or the last bit of the dat file or the log file. Then you can see already that we have 600 time steps, and then the simulation terminates with a total number of particles 1000 that were active all the time, and they had 38 reflections with the wall. So if we go out of this file and go back to ParaView, then we can maybe visualize some motion. We would like to see some motion of particles. So now I loaded the whole list. Then I can hit apply and go to glyph, do the same thing again, spherical particles, no orientation or no scaling. Then you can put here 0.04, so we put earlier, and then maybe you can choose all points, and it gives you, doesn't sample your package or your swarm of particles, and then it hides some of them. But then you can this way guarantee that all the particles that you have injected in the domain are visualized. So we hit apply, then you can see all the particles. Can maybe paint them into, let's say, yeah, I guess red is a good color, so you can see what's happening, at least here in this arrangement. And if you click on this button, which is play, it will play all of these 19 time steps, and it will show you the progression of the solution. Wow, that's really nice, and it's very pleasant to see that particles were actually sampled in a reasonable time window. So you can see already that particles are evolving, some of them are going up and down, and you can see already that there are a bunch of them are very close to the wall. So it's, yeah, I mean, this is maybe part of them, or let's say less than half the diameter. It's about the radius of the particle. If it is exactly the radius of the particle is at the wall, is at the node, so then this particle is considered as impacted on the wall already, which means that it goes back to the domain again with the same energy. So yeah, it kind of makes sense that there were about maybe 38 reflections so far from these particles up and down, and you can save this animation as we mentioned earlier, that if you go back to the initial time step, maybe, I don't know, if you want to use a black background, then you can also have that option. But if you don't like it this way, then you can go back again to white or printing. You can also make as many views or renders as you want. You can here render the same view again. Maybe you can visualize, I don't know, anything. You can maybe see it this way. Let's say if you want to visualize the particles, but at the same time you want to see, instead of the domain, you want to see only the boundary file, let's say here. And again, you have these this no slip boundary condition, and at the same time, since it's 0, the velocity, then it's colored in a good way that can kind of represent what's happening. And maybe let's adjust them both to the same camera. So I don't know if you want to use it this way, or you can maybe also go to this field and say that we want to have X direction positive to the right, and maybe this way can show an isometric representation. So if you want to use the same color for particles down there, you can go ahead and do it by choosing red again here. Sorry, maybe I chose the wrong signal. But here, yeah. So I guess it's just that I didn't click on it the first time. But maybe we don't want to use the same camera, but maybe here we're just showing the streamwise direction, and here we're showing an isometric profile or an isometric view that shows the 3D element of the domain, but at the same time it also kind of zooms in a bit on the transport of particles during the domain. So if you click play, you can see already that particles are going in that direction, right? You can maybe visualize this view down there with the particle velocity, for example. So velocity magnitude here is the particle velocity, if that's an interesting thing for you. And then for the color palette, maybe you can switch this off so you don't confuse things, because the velocity on the upper and lower walls is 0 anyway, so there's nothing very interesting to see. Maybe you can see that you can choose the same color scheme probably if you like, but here in the glyph, so you can have some consistency in the generated pictures. So you can see here now it's a really nice representation, because if a particle is approaching the wall, then it tends more to have a bluish value because it has a very low velocity close to the wall. Then you can, if you like also this idea, you can have the same representation over here. So if you go to velocity field or velocity magnitude, you can see that particles that are close to the wall are impacted by the slow flow or lazy flow close to the wall, because then because there is no slit boundary condition imposed at those walls. And towards the bulk region or the center line of this channel, you have more or less a red color that is represented like this here. So it's up to you really how you want to visualize it. As I said, maybe in the boundary file there is no need for this guy. And yeah, if you want to see this view in an animated way, or a GIF, let's say, you can save these screenshots. Let's say you create a folder that's called animation. Go ahead inside and then test. Maybe the baseline name will be just test, or let's call it particulate channel, and then it will call it particulate channel 0001 and until 19 with the names to time steps. Click OK, then we say save all views, because we want to save this view up here and the lower view as well. Then you can increase also the resolution so you can have a good quality picture, and it will start saving when you click enter. I'm not sure if it's saved already or that I'm missing something, but we can go and check for ourselves. So there is an animation folder that was created, but I'm not sure if we have something inside. We have only one picture. Sorry, I made a mistake. I said save screenshot. So you shouldn't use this except if you want to see just a screenshot. Obviously I just made a mistake, because I should have used save animation. You should have used save animation, but anyways, it's good also that we see the screenshot that was saved. Just from the terminal you can write open and then the name of the file. If it doesn't work with you or it gives you an error, maybe you need to add open xdg, the viewer of the PNG images, or also GPG. And in this way, maybe you don't even need the and sign, but you can see in my case xdj doesn't open, but for me open is enough only to see the screenshot that I've saved. Now we go to ParaView again and just click on save animation instead, and then let's say I want to call it, not to confuse it with this one, I want to call it something else, test, because then we can create a GIF and it doesn't confuse it with this image. So if we hit enter, it saves all views. Then maybe we can raise the resolution a bit to have a good quality. Then you can see already that it's saving quickly those frames or these time instances, right? If you go back to the terminal here, maybe we can delete our part channel, but yeah, anyways, you can also leave it. And with the software that we talked about maybe in the first module or second module, which is Convert. That is a tool. It's not a software, but it's a tool from Image Magic software that we downloaded here, or we installed together through the terminal. And then one of the tools is this Convert that takes all the PNG images, packs them up, and puts them into a GIF format, which is really cool. And you want to gather all the files, and by putting this asterisk you can do that you cluster all of them, or you say basically every file that starts with test.00, which is all the files here in this list, I want to have them and then operate on them some conversion into, let's say, particulate channel .gif, and then you give it the extension. Now it will take a few seconds to generate the file for you. And now it's done. It had generated already the GIF file for you. So you can also use the option open, and you can say particulate, and we open this guy. You can see already that it has generated the GIF for us, very smooth and nice. And what's good actually about the GIF is that if you have a very small animation that it's, let's say, taking a couple frames, like in our case here, the GIF gives you a more continuous image of what's happening. And since it's also a periodic domain here, we have a periodic channel flow, then what gets outside the domain here gets entered again from the beginning, or gets copied to the beginning of the domain, so it can simulate an infinitely long channel. So in this case, a GIF is really good for us, or a very nice tool to have, so we can represent more or less what's happening, because it's a loop of particles motion. It gives you really a good representation. I guess that's all what I wanted to share with you about this case. I hope you could really benefit from this case, and it taught you something new. It's as I said, it's one of my favorite type of flows, and I hope you enjoyed it too. And also please ask me questions, try to make all of these exercises by yourself. Just make sure that you got a good grip on the problem and the dynamics of the flow. Also, you know how to tweak maybe the time step, or you can play around with the turbulence level, what's the input, what's the output, put different boundary conditions and see what works for you and what doesn't. You can increase the particle size, and you can maybe put an initial velocity for the particles instead of being released from rest. So all of these options you can play around with to train yourself on how the code works. And yeah, as I said, we're just scratching the surface here about particulate flows, and you can always learn more and more. Thank you so much for listening and watching, and I hope that you really benefited from this course.